Yeah. Hi, guys. Yeah. Let's start. So we are here to talk about efficient data management in GlusterFS using databases, and who we are here. Myself, Joseph Fernandes. I'm a senior software engineer working for redhat storage out of Bangalore. My colleague, Dan Lambright, he is a principal software engineer for redhat storage working out from Westwood. Okay, the agenda. The agenda is we'll have a quick overview of what GlusterFS is. We'll understand what data maintenance on a file system actually means. What are the challenges with data maintenance? What are the existing solutions that we looked into? And what is our proposed solution to have efficient data maintenance? We have a case study, our own feature, data tiering, the lesson which we have learned out of this activity, and what next? So, what is GlusterFS? GlusterFS is a distributed file system. It's a software-based NAS, network attached storage. It has multiple nodes which actually participate in a cluster to provide one single namespace which can be accessed by multiple Gluster clients or NFS or SMB. It works on TCP/IP and RDMA. Well, what is data maintenance? Now, when we talk about file system, especially a distributed file system, you have all your data that is scattered across your cluster. And you need to run maintenance tasks on your data for data protection, for performance, and optimal storage utilization. For example, for protection, you can think of a compliance use case. Your storage might be used for certain compliance cases where you need to retain your file for certain amount of time where it is immutable, undeletable. Or our own use case of data tiering, that you have segregated your storage into hot storage and cold storage. You have, when I say hot storage and cold storage, hot means faster, cold means slower. So that is for performance and storage optimization. Now, there are many other data maintenance tasks that you can run. One thing that is common in all data maintenance tasks is they are heavy. You don't run them very often. They are heavy on your CPU, memory, and network because it's clustered here. Now, well, you can't change the nature of the beast now. What you can do is you can optimize on the search options. Identify the data set which you want to do data maintenance on. And there comes a faster search. Do a quick search before your data maintenance task, which is a scheduled task, and identify what you want to do with that data. So you need to do a fast search. To do well, most of the data maintenance tasks that you look into, like tiering, for example, you want rich metadata of the file. Just M time wouldn't be sufficient. You would, your question may be, get me all the files that have changed during last 6 hours so many times with certain frequency. And this you will not get in any usual file system, POSIX file systems. So you would require this rich metadata to ask this question, to query this. Next one is, well, we are talking about distributed file system. So our search should cater to this. It should be distributed in nature, plus proper load balancing. You don't want one particular server running sequentially, file by file, picking up files and doing data maintenance. That will be awfully slow. Now, the thing with data maintenance is, as it is heavier on your resources, you do want to run data maintenance on your peak I/O load. You would take it, for example, usual backup scenarios, you will be having backup windows in which you would want to do backup. In the same way, you want to do data maintenance during that hours. Well, The existing solutions which we actually looked into for searches were file system crawl. Now, the problem with the crawl is you can optimize the most when you're talking about standalone. But when you're distributed, what we saw is most of the time the network was clogged with stat data. You do ls, you go into the file, you do another ls, go into directory, and so on. So that was not a feasible option, and we actually had few data maintenance tasks which were using this, and the performance was not up to the mark. So we thought, let's look into file system logs. We have our own change log. The problem with this is, though it is fast in recording, to query this log, because it is too huge, to query something again and again, it would be, you have to go through the whole log. That is the first thing. Second thing is, you're not going to keep that log forever. For a retention case, where you are talking about, get me all the files that have not changed for 100 days. I can't use a file system log for that, because my logs would have, since they are circular in nature, they would have been refreshed or rewritten. Metadata servers. Gluster doesn't have a metadata server, so there's no option for that. In-memory inode caches. In-memory inode caches are really fast, but the only problem is they're not durable. If there is a system crash, all that intelligence which you have put there is gone, poof. So we couldn't use it. So our proposed solution is optimized DBs for GlusterFS. Now, when I say optimized, what are they optimized for? Our motto is record now, consume it later. Record as fast as you can, a faster write, and then with good querying capabilities, query it later. Because your data maintenance tasks are going to run at the end of the day, or might be twice in a day, or so on. Plus, I want least management of a new component. Gluster itself, since it is distributed, if we had gone for another service, a database service, there would be an extra overhead over the administrator to maintain that. So we used an embedded DB. So the embedded DB which we used was SQLite 3. And I'll tell you why we used it. Well, now to use the database, we actually wrote a new component called as libgfdb. Now this gives you an abstraction of what database you want to use for this purpose. Today it is SQLite, tomorrow you can go for NoSQL, or tomorrow no database at all. You write your own data store. So this gives you an abstraction, so you have the flexibility. Plus, this libgfdb actually provides you options to record rich metadata or calculate. So you can put in whatever filters you want to calculate and get stored on your database. Plus, it is non-centralized. So in Gluster, our basic storage unit is a brick. So you can consider it as a storage node having multiple bricks over which the namespace is covered. So each brick is going to have its own database. What's the advantage? You don't have a bottleneck. So if one brick goes off, it's okay. Your namespace didn't die. Your other databases are up there. Of course, you're going to lose the data that was there in the brick, but you can still reuse, you can do data maintenance on other bricks. And the last part, which this is a futuristic thing, we are going to add performance optimization on libgfdb. I'm going to talk about it a bit later. This is a vanilla Gluster stack. So you have a Gluster client. The good thing about Gluster is it is all stacked up. So if you want to add a new feature in the file system, write a library, put it in. So that's a client stack. This is a server stack, and this is the last component here which actually writes to the actual storage. What we have done is, on the server stack, at the bottommost, before the storage, we have added this. It's called CTR, change time recorder. Now, what this does is, this actually intercepts the IO whenever it is coming down, does the calculations quickly, and pushes that information to the libgfdb. The libgfdb is going to write to the database. Okay. The first question is, why are you doing inline? Will it not affect your IO? Well, we have optimized, as I've told earlier, we are recording it fast. Okay. So what we have done to it to record fast, I'm going to talk about it later. So over the time when all this gets accumulated, you have your schedule scanners that will kick in. They will make a simple query. For example, for data tiering, you will just ask this question, get me all the files that have changed with this frequency on a cold tier, so that if I consider them hot, I will move to the hot tier. Now, this one thing we should understand in data tiering is not a cache. A cache would be faster, a block cache would be faster. We are talking about whole files to be moved. So if I do that activity in actual peak workload, it will bring down my performance of actual IO. So I do it offline. So offline or during a period, during a window. So these scanners will go and ask the database, get me all this, and it gives you a big list. It takes the list, starts working on it. And this is per brick level. So every brick, it's going to ask the same question. Get me this, and I'll start my work. Now, why SQLite 3? SQLite 3 is small, it's embedded, and it gives you performance optimizations like this. So we wanted to record it fast, so we actually contacted the SQLite user, the community there, and they helped us with all this optimization parameters. First of all, align your page, your SQLite page, to the system page, like 4 KB or whichever it is. Increase the cache, and this is very important, the journal mode. Now, usually, whenever you do an insert into a database, it would actually take you there using the B tree, index it, and then write it there. Write it onto your actual location, into the record. What Wall does is, it's write-ahead logging. It writes onto a log file. So whenever you do an insert or an update, it is always an append. Sequential. When you're sequential, and most of the time it is not, I'll put a star there, most of the time it is non-indexed. So it just writes, records, okay? And what is checkpointing? Now, this log actually builds up, and after a certain point, all of this is taken and flushed into the database, and that is what is auto checkpointing is. Now, auto checkpointing has a problem. It actually slows down the database because it holds the logs, takes the whole thing, and pushes it down. We don't want that to happen very often because that would block our insert threads. So we make it during or just before the data maintenance schedulers kick up. Of course, it writes asynchronously onto the cache. And what is auto vacuum is, this is fragmentation of your DB file. So you're done deletes, there are vacuums there, you want to clear it off. All this maintenance operation will happen later. Now the question comes here is, if you're having this big cache, what happens if there's a power outage? Gone. For most of our metadata that we calculate, it need not be durable. Heat is almost a function of time. So heat is relevant with this time. So if that information is gone, the machine comes up. Those files are going to be heated because of your workload is like that. If you're using file 1.txt now, if the machine went down and you're back, you're going to use it again. And that is your pattern. So now, a bit into what SQLite does and how it really helps us is, whenever an insert comes, it goes into the cache, buffer cache, which we have provided. Of course, it uses a shared memory because SQLite provides access for multiple processes. So it does that by using a shared memory. And this gets synced later on. Of course, there is a sync parameter. It gets synced into the write-ahead logging. So it just appends here. And after a point, during the checkpointing, it will take, first of all, it will flush the buffer, write it here, take this whole log, and then put it onto the database. So that's why you want auto checkpointing to be less often. Might be at the end of the day, might be after like 12 hours or so. There is a chance where if you have delayed your auto checkpointing, your wall file, it's basically a file, it's a log file, may grow a bit big, but that's okay. That's okay. Because what we have tested is it may grow to 1 GB when you are talking about terabytes of data that has been inserted. Okay? Now, my colleague Dan Lambright is going to talk about our feature that we developed, the actual implementation.
Okay, so Joseph made a service which stores data related, metadata basically. And this is an application that's coming out in Gluster 3.7 that we're writing together, which uses that service. It's going to add tiering capabilities to Gluster. And when I say tiering, what I'm basically talking about is a logical volume or logical namespace exposed as one namespace, but internally has possibly multiple different storage units behind it. And data is moving between those storage units according to different policies. There's lots of different types of tiering implementations out there. You could have a storage unit which is secure and another one which is not secure, or compressed or uncompressed. There's different ways. We are, in 3.7, introducing cache tiering. And this is a very timely feature. It's timely, even though this has been around a while, the tiering, because of solid-state disks. We want customers to be able to use solid-state disks, but we know that they can't necessarily replace all their hard disk drives with solid-state disks. So this is a way that they can use a solid-state disk incrementally, maybe to help a single volume that's slow. They can add a solid-state disk to it, and it would act as a hot tier, the cache data that's popular. Another reason why this is a timely feature is with the advent of erasure coding. Erasure coding is a really important way to reduce the cost of the storage that you buy. And the price you pay, though, is that it's slow to do some of the calculations to do it. And you can do the same trick as you do with SSDs. You could put some fast tier on top of the erasure coding. This is actually a trick that Ceph did, and we are mimicking that. And I'll have some more to say about that shortly. So what goes in the cache is really driven by the scheme that Joseph has invented. We use a database to track usage patterns. We store when IOs arrive, and the timestamp is how we know the frequency of whether data is popular or not popular, and then that drives the migration. And the migration is a slow process, as we mentioned earlier. Because it's slow, because migration is physically moving a file, we work at the file level, of data from one storage unit to another storage unit. We want to be smart about the policy of when to do this. And so we've had, fortunately, a lot of other tiering implementations at Red Hat. There's one in the kernel called DM Cache. I mentioned Ceph already. So these seem to be some of the better tuning knobs to drive the policy. We can choose the file size. Of course, if you have a very large file and you're only going to touch one little piece of it, you might not want to migrate large files. You might only want to migrate small ones. Or you might have a policy which says, I have an SSD. SSDs only work well with random I/O, not so good with sequential I/O. So you can detect when the I/O is random rather than sequential. DM Cache takes a shot at that. The access rate, if the data is only touched once, you don't want to do an expensive migration. Gluster, hopefully, for 3.7, will have a feature called sharding, which is where we basically take files and we split them into chunks, settable chunks, and therefore we wouldn't be migrating whole files, we'd be migrating sub-file granularity. And that'll be great. So here's how we use Joseph's system. Well, actually, I'll get to that on the next slide. Here, okay, so this is basically, we've got a new volume type in Gluster. It's called the tier. As I said, you can attach and detach tiers dynamically to volumes. So you don't have to permanently give an expensive SSD to a particular volume. You can detach it and add it to another one later as it's needed. The migration of the moving of a file from one to another is based on existing mechanisms, which are relatively robust. The Gluster uses a dynamic hash table to decide which node to place files. We've modified that such that for the tiering case, rather than using a dynamic hash table, distributed hash table, excuse me, we go to the hot tier first. Always check to see if the file resides on the hot tier. If it doesn't, then we go to the cold tier. Writes always go to the hot tier as well at the moment. Of course, the tier itself may be composed of multiple bricks. And for data placement at that level, we do use a dynamic hash table. And we call this stacking DHTs, and you can actually create fairly complex graphs of DHTs, and that's a feature for 4.0 that's coming. So this depicts how tiering works. At the very top, you have the client with the tier translator. Translator, again, is like a driver. And it has a split fork, hot data, cold. On the hot, it would go to the hot server. The key point here is this CTR translator. That's a change time recorder. It intercepts IOs as they come in and records in the database the time. And then there's a background process which queries the database, finds the data that meets criteria according to those policies from the previous slide, and instigates promotion or demotion between the tiers. So how well does it work, the tiering? This is an interesting problem too, because existing benchmarks mainly were developed for memory caches, and they don't work too well for tiering caches because the price of a cache miss is so much greater. When you have a cache miss, you have a migration event, which is much worse than a memory cache miss. So what you really need is a new type of benchmark which has more stable workload. That means, when I say that, I mean that the data will stay on the hot tier for an extended period of time. Data cannot move quickly between the tiers. That's not a good use case for us. That's not a way to use a cache tier. More like it would be something like, say, some videos that are popular for, some movies maybe, that are popular for a few days, few weeks. They reside on the hot tier during that time. When they become less popular, they migrate to the cold tier, and new movies replace them on the hot tier. So anyway, we've built a new benchmarking tool in Red Hat in the performance group, which is very promising to that end, to look to benchmark cache tiers, and I think it would work well for DM cache and Ceph as well. Initial results, we're just getting started. It's going to take a while, but we do note that there are some scalability issues with the database. But fortunately, Joseph is to the rescue. Here he's flying in right now.
Yep. Yes, so the scalability issue. These are the lessons we have learned. First of all, a few of the DB updates which we do, when I said record fast, if there is a DB update for, suppose that we are counting how many times a file was accessed, it's a counter. So there is something in the database to fetch it, +1, put it back. If you do that, it's an expensive operation. When I just go back to the slide, here, when you're writing, it's fast. But if you're doing a read in this path, it's awfully slow because it has to search there, here, here, collaborate, and give back. Right? So if you're doing read, modify, insert, or update, that would be slow. And for that, we have a solution. The next slide will talk about it. Next one is scalability. SQLite is just one single file. As it grows, your queries, if you're, for example, my recording was 1 million records, it took me 1 minute. And when it's growing more and more, we'll hit that. And I think even OpenStack Swift also are facing scalability issues. So there is a solution to that. There is a proposed solution to that also. Next one is, if you are looking at metadata that you want to have durability, the ACID nature, well, that would be a problem because as we write fast, we're using a lot of cache, and if that cache goes off, for example, if you want to remember the paths, the hard links, don't rely on this database. This is not a metadata database. This is for data maintenance purpose. So those are the few drawbacks. Now, solutions. So the first problem is few things are expensive, a few updates are expensive. So we will introduce something called as a plog in our library. Now what this will do is, it's a circular log. So, and this I have got from the SQLite community also. So they told me that instead of using the wall, which is a log file, but it will eventually do some indexing. Even if it is a wall, if I do a double insert for the same primary key, I'm getting an error. That means it's checking somewhere. So that check may reduce your performance. So we are introducing a plog, which would be above all the databases in the library, which is a circular log. The log itself is divided into batches. So there will be insert threads that will work on it, and as a batch is full, it will be flushed onto the database. So always, any inserting thread will get a location where it can write. Next one is the scalability of a single file. So what the solution we are thinking of is shard the database. Locally, you can have, and that's configurable, how many database files you want to have. And each file in Gluster today is represented by a GFID globally. So you say, it's like a hash range. So you say this GFID goes into this bucket, this GFID goes into this bucket. So it's basically divide and rule. So in that way, your searches, you know that if you want to search something, you're going into that bucket and you're going to search there. We are also looking into Ceph steering implementation of Bloom filters, how they are doing it. There are few things which we need to work on. There are a few points which we need to work on, but I think, yeah, it's better to give it a try. The cool thing is, because of this libgfdb, none of my translator, that is CTR translator, neither the scanner has to change anywhere. They are going to call the same function calls, agnostic to what store is below. Well, this is a feature page. You can go there and read about it. Right now, this code is not upstream. We are maintaining a separate forge as we are doing development. Eventually, we have a deadline to put it upstream. Yeah, and these are our mail IDs. You can send hate mails to that. And thank you. Questions, please. Correct. So, well, right now, the data what we are saving is the access time, the read time, the access time, the change time, and the counters. If we are, there is a problem with Gluster. By just using the GFID, you may not, for like tiering, we would require a path or links. So to record it safely and in a durable way, we are looking at that options. I mean, in the library itself, not in the database. The database, we are not going to change any tunables there, neither we are going to add any code there. So we are looking at options. Well, it's reads and writes. Okay, I'll specify what we are doing there. For writes, we are having metadata and data. For reads, only data. Stats won't count. Get exatter won't count. No, independently. You have two different counters, two different, right. So the reason is, in tiering, we would give an option. How would you define something is hot? So these many writes during this time, these many reads during this time, goes cool. The cool thing about SQLite is you can, the beautiful query language. So you can do mix match things, it's nice. Right. So if you start hitting where you start moving files in and out, that's all you're doing because it's so slow to move a file. So is there some way to kind of throttle that? Well, we are looking at options. Today, our data mover is, since we are a user land file system, we do kernel switches. So if I want to read something, I have to go to the kernel and via the translator, we call it a railway. So the whole rail route, go and fetch it and come back, and we do a awful 7 kernel switches for a block of data to be read. Actually we are looking into a POC where we can do zero copy. So you know the socket, you know the FD, and use zero copy or any kernel optimizers to just send one shot. So that's what we are looking at. Well, this is more the nature of data movement we are talking about. The time which we can save on getting the data set, identifying the data set that you want to move, this is actually reducing that. But of course, we are looking at in that direction. Yeah. There is another use case which I missed out was bitrot. In Gluster 3.7, we are going to have a bitrot feature, basically whether the data which is there resides on your whole namespace has gone bad. So it's they can use this. So. Okay, do we have time? Okay, fine. Thank you.